So the first thing we're going to do is we're just going to define a couple of things. So what we just discovered in the warm-up, or hopefully that you were able to get, is that if one event occurs m ways and a second event occurs n ways, the number of ways the two events can occur in sequence is m times n. And so that was the shirt, pant, shoe combination, or 3 children being born. Okay, this can be extended for any number of events. We did 3 in both cases of the warm-up. And so we have we're purchasing a new car. The possible manufacturers, car sizes, and colors are listed. So we could get a Ford, a GM, or a Honda. We can get a compact or a midsize, and we can get that in white, red, black, or green. We want to know how many different ways can you select one manufacturer, one car size, and one color, and we're going to use a tree diagram to do this. Okay, so let's first just use the fundamental counting principle that's up here. We have 3 different car manufacturers, we have 2 different sizes to choose from, and we have 4 different colors. And so altogether I should be getting 24 different car choices that I have. So I have 24 different cars to choose from. Using a tree diagram, what this does is we actually draw out all of the possibilities using a tree. And so here's the tree diagram here. So we have first at the top of the tree, we have the 3 choices for the car manufacturers. And then for each car manufacturer, we have 2 car sizes. And then for each car size, we have the 4 colors. And if we count up all of the bottom branches of this tree, that gives us the total number of ways that we could have found or gotten a car. And so we see it, we have 4, 8, 12, 16, 20, 24 different ways. Now, clearly this is faster to just multiply the numbers together, but you may be asked to create a tree diagram. I'll make sure it's not 24 different ways, but you may be asked to create a tree diagram, and you should be able to at least read what that is and know how many combinations there are from that tree diagram. So here's another example. We have the winning shopper. Excuse me. To promote the new West Side Mall, the mall manager gives away a store gift certificate. The winning shopper chooses the store by picking a piece of paper from a box. The box contains the names of all the stores at the mall. Below is a list of the stores excuse me, at the mall according to category. So there's 8 audio video shops, and there's 7 home furnishing stores, and there's 9 toys and hobbies shops. And you can look at all these stores. So the first question is really, how many names does the box contain? So if we add up all of these numbers, okay, which I'm going to use my calculator for. No shame in doing that. I don't want to mess up. So I'm just adding together all the different stores in this mall. I'm getting 170. I hope you're getting the same number. So there's 170 stores. And if there's 170 stores, that means these are the outcomes, okay? It's also called a sample space. But these are all the possible outcomes. So we don't know what the names of the stores are that are audio video stores, but we know there are 8 different shops. And the person who wins could pick any name from any of these stores. Okay. Just double checking that I have the right numbers typed in. It looks like it, 170. So these are called the outcomes. Now, what type of store is the winner most likely to pick? Well, if I look at all the different types of stores here, I can see that the clothing store has 47, there's 47 different clothing stores in this mall. Okay? Because there are more clothing stores than any other kind of store, it's most likely that a clothing store is what the shopper is going to pick. Now, every store in the mall has an equal chance of being picked. There are 170 different stores, and each one has a 1/170th probability of being picked. But if we go by categories or types of stores, then clothing stores have a higher probability of being picked than any other type of store because of the fact that there are more clothing stores than anything else. Now, just because there are 47 out of the 170 that are clothing stores, that doesn't mean that we are necessarily going to pick a clothing store. 47 divided by 170 is only about 0.276. And so that is the proportion of names in the box that are clothing stores. And so there's a 27.6% chance that a clothing store will be picked out. And so that's only a little bit better than 1 in 4. And I would say it's 3 out of 4 times you're not going to be picking a clothing store. So it's possible that you don't pick a clothing store. It's not necessarily going to be a clothing store, but it is the most likely. Okay. Now, what is the probability of the winning shopper choosing a footwear store? Okay, so we're going to express our answer as percent. And in most of these problems, they're either going to ask you to express your answer as a proportion or a percent. The proportion is just the decimal, like we saw on the last one, 0.276. The percent would be multiplied by 100, you get 27.6. Okay, so we have 16 footwear stores in this mall. There are 170 stores total. So 16 divided by 170 gives me 0.0941. Now this is the proportion. If we want the percent, we multiply it by 100 and we get 9.41%. So that is the percent probability that someone would pick a footwear store out of the box. So what are we doing in all of these is I took the number of favorable outcomes. In this case, it was the type of store, so clothing store or footwear store, and I divided it by the total number of possible outcomes. And that gave me the probability. And this is called a theoretical probability. So and this is the notation we use. It's sort of like function notation. We say the probability that, and then we put the event in there. And that's going to be equal to the number of ways this event can happen. So that's the numerator. And that's the favorable outcomes. And then the total number of things that could have happened is what's in the denominator. Now, these probabilities are always going to be between 0 and 1 if we're talking about proportions. 0 is something that's impossible, and 1 is something that is absolutely going to happen. There's no doubt that it's going to happen. We can also write these probabilities as a percent, as we saw already. So let's move on to another example. Okay? So a die is a numbered cube marked from 1 to 6. Hopefully we all know what a die is. And we're just going to find the probability of a couple different things thinking about rolling a die. And we're just rolling it one time for each of these. And when we start, when we move on to the next problem, we're rolling the dice again just one time. Just one die, one time. So the probability that we get an even number when we roll a die once, well, we have to know how many even numbers there are on a die. Well, it goes 1 through 6. So 2, 4, and 6 are the even numbers. That's 3 of them out of 6 numbers total, and that gives me a probability of 1/2. I can write the probability as a fraction, 1/2. I can write it as a proportion, 0.5, or I can write it as a percent, 50%. Now, what's the probability that I roll a single die and I get a 0? Since a 0 is not one of the numbers on my die, then 0 is the probability. This is an impossible event. There are no ways to get 0, and there are 6 possible outcomes, and so that gives us 0 total. Okay? And the proportion, fraction, and percent are all the same for this. It's 0. Now here's the probability that we're going to get a 5 or a 6. So I'm going to roll the die, and I'm happy. It's favorable to me. I'm happy if I get a 5 or I get a 6. And so there are 2 ways to get a 5 or a 6. I could get a 5 or I could get a 6. So there are 2 numbers that would make me happy here. Out of the 6 possible outcomes, gives me 1/3, which is 0.33, or it would be 33.3%. These are all correct answers. If you're going to write a fraction, please do it in reduced form. Okay. If you're going to write a proportion, 2 decimal places is fine. If you're going to do a percent, I would like at least 1 decimal place after the whole number if it is not a whole number value. So 50% is fine, but then 33.3% is what I'd like to see.